So on this lecture, I will be generalizing the wave equation into a three-dimensional space. And of course, the motivation is that we need to, at some point, generalize our description into a really 3D space. So this is where we do it. So I will be introducing to you a component forms of the wave vector k and the position vector. And I will be doing a little bit of calculation of the dot products. So basically the kr dot product will be calculated. I will be derive the wave equation. And then I will be saying a few words about the fact that we would want to have a coordinate-free wave equation so that we would not be restricted into a given specific coordinate system. So for example, not only into a Cartesian coordinate system. And then because of this requirement, we need to introduce to you like a vector calculus operations. So gradient and Laplace operators will be introduced. And then I will be forming the wave equation using the Laplace operator, because that gives me a coordinate-free representation of the wave equation in 3D space. And then finally, I will be saying something about the choosing the right coordinate system depending on the situation at hand. So this is what we will have in mind on this lecture. So I will now get started, since time is of essence. What we want to do here is that we will simply just want to generalize the wave equation, and we want to generalize it from a wave propagating along z into a wave propagating in arbitrary direction defined by the wave vector k in a three-dimensional space. And how do we start here is that we just write the wave vector k and the position r in a component form. So k, the wave vector, can be just written in a Cartesian basis using a x component kx plus along the y direction, and of course hats here of the unit vectors. Ky is the y component of the wave vector along y direction, and the same thing for the z direction. Kz is the component of the wave vector along the z direction. And similarly, the position vector r can be described in its components along the x, y, and z directions. And of course, the notation, I guess, is quite clear, the meaning of it. Now, we want to describe a time harmonic wave, a plane wave. And if we want to describe a time harmonic plane wave, we can write it that the psi is of a form that we have the amplitude a times exponent I kr minus omega t. And this is the description of a time harmonic plane wave. And here we just want to write this dot product, that how it looks like. Of course, we just calculate it in a component form. This is how it looks like. And this clearly shows me that the phase function inside is still a scalar valued number. So it's not a vector or a matrix inside the exponent. So I'm just multiplying kx with x, and I'm adding ky times y plus kz times z into the phase function. And we know that in the 1D case, the wave must be twice differentiable, because that was the kind of requirement arising from the wave equation. So when we are calculating things here in a 3D case, we know that the wave must be differentiated twice with respect to space and time. So let's first differentiate it twice with respect to space. So we take the psi, the wave, and then we calculate the second partial derivative with respect to x. What we get out from here, of course, is minus kx squared times the original wave. So nothing strange there. We have the exponent here. This is a constant. So that doesn't change when we calculate the derivative, the partial derivative. So only thing is that we have this ik out when we calculate the first derivative, and when we calculate the second derivative, we have another ik out, so that we have the minus sign at the front, and then we have kx squared. The same thing, of course, applies for the other directions. So similarly, we calculate the second partial derivative with respect to y and z, and we have exactly same kind of results out. And we can combine these three partial derivatives together, so that we can just write things that all three partial derivatives added together, they result in on the right hand side, when we are now adding the kx squared plus ky squared plus kz squared together, and then we still have this multiplying the original wave. So this is, we just do this mindlessly for now, and I will be shortly motivating to you that this actually helps in forming a generalized wave equation, and then we have this original wave here. And this guy, physically, we see it that this is exactly the modulo square of my original wave vector k. So I can just write this inside the parenthesis that this is k squared times psi, because this is what it is, of course. It's a vector, and its length can also be calculated by just adding the modulo squares of the different components. And now let's next differentiate our wave twice with respect to time. And now we have the psi, and we take the second order partial derivative with respect to time, and what we are left is that we have minus omega squared times the original wave. Same kind of functional form with respect to time, so we already know how do we calculate this. And omega squared can be written differently, so of course we can write omega squared as a k times v squared. So this is what we have. Please remember the phase velocity of a time harmonic plane wave is omega per k. So omega, of course, is the velocity v times k. And we combine these different spatial and temporal parts together, and we can now form something that looks like our original wave equation. So on the left-hand side, we have the partial derivatives over the spatial coordinates, and on the right-hand side, we have 1 over v squared times the partial derivative of wave psi with respect to time. And this is our three-dimensional wave equation in a Cartesian coordinate system. So this is really that fulfills and gives me a time harmonic plane wave as a solution, as the simplest of solutions. You can verify it yourself, that you just verify that this equation can be solved by just using an ansatz that psi is a time harmonic wave. We just did that, and this is what we get out. And now we can clean the notation quite a bit by just using differential vector operators. So especially at this point, it's good to redefine, or not redefine, but reintroduce to you a gradient. So the triangle upwards, and this is an operator defined that we take the partial derivative along x, and this is a vector operator. So this is the x component of my gradient, and then I have my y component of the gradient, and the y component is the partial derivative with respect to y coordinate, and then I have my z component, and that's the partial derivative with respect to the z component. So this is my gradient operator, and this is a vector valued operator. So really, please note that we have vectors here. So it's not a scalar operator, but it's a vector operator. Then we can also define a Laplace operator, so a triangle now squared. And basically this is defined that we first take the gradient, and then we take the dot product. So we calculate the divergence. And this is defined that it's the second partial derivative with respect to x plus second partial derivative with respect to y, and plus second partial derivative with respect to z. And this is known as a Laplace operator. And now, look and behold, this is a scalar valued in a sense, so that depending on the kind of type of the wave, we can either apply this into a scalars or vectors depending on the context. So that we may have either a scalar valued Laplace or a vector valued Laplace operators. Please note that it's quite general in nature. So using Laplace operator, the wave equation that we just discovered, we can really nicely write it in a compact form. So we have a Laplace operator operating on our wave psi, and on the right hand side we have 1 over velocity squared times the second partial derivative of wave with respect to time. And the nice thing about this, of course, it's a more convenient, shorter notation, but the special advantage is that now our wave equation can be transformed into other coordinate systems easily by just writing this Laplace operator in the corresponding form in the different coordinate system. So in essence, what we get now is that we have a coordinate-free representation of the wave equation. So this is something that the original equation did not give us. So now, since we do have the Laplace operator here, we can describe the wave equation either in Cartesian coordinate system, or we could also describe it in a spherical coordinate system or in a cylindrical coordinate system. So this is the kind of benefit we get when we are introducing the Laplace operator. And we would just need to know how the Laplace operator looks like in a different coordinate system, and then we would be able to represent things differently. And then subsequently, like in case we are getting in the next lecture into the spherical waves and cylindrical waves, this is incidentally exactly what we would do if we would want to derive spherical wave or a cylindrical wave. So we would transform this wave equation from the Cartesian coordinate system into, let's say, spherical coordinates, and then we would solve that differential equation in that coordinate system, and the solution would be a spherical wave. The same thing we would do if we would want to find out how do we derive a wave of a cylindrical wave. How that looks like is that we will transform our wave equation into the cylindrical basis, and then we would solve that differential equation in that coordinate system, and we would get a cylindrical wave out as a result. So this is what we could do in case we would want to do. But here, of course, we do not make those derivations. They're slightly mathematical, so that's deemed beyond our scope. And of course, in this scope and in this context, we do not go into here, but in many cases, when we want to describe electrodynamics, radiation of electromagnetic radiation in a more arbitrary way, we might need to change our coordinate system from a Cartesian basis into something else. But in this course here, we really mostly only need to be dealing with Cartesian coordinate systems. This is perfectly adequate for us. And most of the time, this is even the smartest of choices, but sometimes you may need to come up with a different basis and a different description. Just depends on your system. And here, my main message I want to end up my lecture with is that please always think of the problem at hand. How does it look like? So if you have your problem that looks spherically symmetric, and then really probably you want to also use mathematics that has this kind of symmetry implicitly inside the math, so that you don't need to do kind of like bubblegum complications into your math. So please always think about the symmetries of your problem and of your system, and then subsequently choose the appropriate mathematical framework. This is what I wanted to say. So thanks for following me. And next, I will be introducing spherical and cylindrical waves that we could, of course, show easily now that they also fulfill this more general wave equation. Thanks for following, and bye-bye.